Well, hello everyone. Welcome to another high dimensional probability reading stream. So yeah, we left off at 2.3.5 last time, so just in the middle of the Chernov chapter, or subsection, or section, I guess. It's a binary search on the levels of organization. Yeah, so I think today it will be sort of a short stream, maybe like a tight half hour because I have like a meeting later. But I think we can get through the Chernov chapter. It's just 3 exercises. So let's get started. So yeah, the first one. So what's it saying? It's saying that if you add up n things in like the context of before, so like you add up n things where the total probability of one thing is equal to mu, or yeah, the mean is mu. And then the probability that you are a distance from the mean proportional to delta is exponentially small in delta for delta between 0 and 1. I wonder why you have to stop at 1. So I noticed at 0, then of course this probability should be like 1. You don't get 1, you get 2, presumably because there's like a two-sided bound, so it's like a pretty bad estimate near delta equals 0. And then I guess at 1, things start being like impossible. Like I guess you can't be more than like the lower tail, I guess, goes to 0 at some point. Like you can't be more than mu below because this is of course a positive number, but then it should just be an overestimate. So I don't really know why we need delta less than 1, but let's just jump in. So yeah, they say just to kind of do it by doing it. So yeah, we've got two Chernov bounds for the upper and lower tail, and we're just going to combine them, and hopefully we get something that works out. Though it's 3 coffee cups, so maybe there'll be some twist. Maybe it'll end up being hard. So let's see. So the probability. Oh, oops! I opened this with the wrong program. I opened it with my PDF viewer. I need to open it with my note taker thing. Okay, right, here we are. Okay, so we are. Oh, so when I resize it, scrolls a bunch. Okay. Okay, so we've got our 2 Chernov's inequalities. So the probability that we're trying to bound is the probability that Sn is a distance from the mean greater than or equal to delta mu. And of course, this should be the probability, well, I guess less than or equal to the probability, maybe exactly equal, but whatever, I'll just say less than or equal to the probability that Sn is greater than or equal to 1 plus delta mu, plus the probability that Sn is less than or equal to 1 minus delta mu. And now each of these things can be analyzed with the Chernov bound. So the Chernov bound is just an exact thing that holds for all n. So we can just plug it in. So we've got this one, which is the one given to us, and then we've got the one coming from the exercise, which is exactly the same sort of. So yeah, let's plug in and hope for some cancellation. So we get the same e to the minus mu in both cases. Maybe I'll just factor that out. And then this plays the role of our t. So what do we have? We have e to the mu over 1 plus delta to the 1 plus delta plus, yeah, remember I factored out the e to the minus mu, plus e to the mu over 1 minus delta to the 1 minus delta. Okay, so I think this should be exactly it. And now what is our goal? Let me put it next to the problem so we can remind ourselves what we're aiming at. Okay, so here's our problem, and here's the bound we have so far. So we need to show this is less than this. So how do we do that? Okay. So kind of want to split this up into like a delta term and a minus delta term. Or it says to analyze the bound for small delta, so I wonder if like we want to make some kind of Taylor expansion type thing. Like maybe the idea is for small delta. I also notice it's funny that this is being multiplied, because I would expect it then to show up like additively in the exponent, but maybe this is just supposed to be dominating it. Though I guess it. No, I guess it. Yeah, like this whole thing is this, and then you throw out this to get like an overestimate, maybe. Okay, so let's get more space. I'm gonna insert a page. Is it crashing? Okay. Doesn't seem like it's crashing, but it's not starting a page. Is it working? Let me just restart it. I've noticed sometimes this program crashes when I try to insert new pages, so I'll just force quit it. Okay, so we're going to get like an e to the mu term from the 1. Like we can factor that stuff out, I think. Yeah, so I want to split it up into like the 1 exponent and the delta and the minus delta. And then we can like factor some things out to the front because they'll be common, like the e to the mu. It's not quitting. I need to like bring the heavy guns. So this is 10.315. What? It's right there, right? Or do I need to like specify PID? Yeah, I don't know what argument kill takes, if it takes like PID or yeah, it's supposed to take the PID. Okay, wait, how did that not work? So now I can't switch tabs in this terminal. This is not quitting. This is annoying. The stream looks like it's still running though, so that's good. I think. It might not be. Well, oh, thanks, Pseudomaze. Wait, so does kill not take a PID? And oh, okay, so this is like a okay, so that was a program that would kill it by name. I cannot like close things. I think like my whole operating system is like freezing up. Okay, I think I might just have to like restart my computer. This is very strange. Oh, thanks for the follow-up, Puck3131. At least the important things are working. I hope the developers of External are watching this, because this has happened before when I tried to add a page to an existing PDF, but it worked like earlier with this textbook, like yesterday, so I figured it would be safe to do it on stream. But I guess not. Maybe the problem is I had this highlighted when I tried to insert the page below. Yeah. Well, we can just like think about it. So yeah, I'm thinking we'll split this up by 1 plus delta and 1 minus delta. And then there's a lot in common, the e to the mu, so I'll just factor that out. So we'll get a e to the minus mu plus 1 times mu, and then you have like you have e to the mu delta plus e to the mu minus delta. Okay, and I think it's the same sort of thing that we've seen before, where if you okay, and I might even just throw out. Oh, well, I guess you can't just throw it out. Yeah, I think I'm gonna have to turn off my computer. Can I start a new terminal? Oh, hey, Jack. Oh, okay. Nice to switch your name. It's good to see you. Yeah, I guess the stream is dying. I don't think I can start a new terminal. If I type Control Alt C, oh no, I can start a new terminal. Okay, I just can't close the terminals I've already started. Okay, and then I can run top so we can see the names of things. And we can see that external PP is still 10315. Isn't that what it was before? Yeah, and then it says there's no such process. Does that make sense to you? Okay. What should I run in my terminal? I'm always down to copy and paste code from the internet into my terminal. Oh, you want me to kill Chrome? Oh yeah, okay. I guess I don't need to keep Chrome running. It probably is what's taking most of the stuff. Okay, so wait, if anyone chats for the next 5 minutes, I probably won't see it. Oh wait, I think we just finally got it. Okay. We're saved. Okay. Oh yeah, I guess you can see OBS is taking like most of it, and Chrome. I should probably close some tabs before I start the stream. Okay, I guess it just took forever for like the PDF viewer to die. Okay. Let me just immediately reopen it. I'm sure it'll be fine. Okay, thanks for telling me about this PID of command. I actually wasn't familiar with that one. Okay, what could go wrong? Okay, looks like it's working. And we've got to be able to annotate on it, right? Oh yeah, I didn't save, so I have to rewrite that equation. Okay, so we had this probability, which I'll call star. Kill -9 PID. Oh, you have to specify -9? I thought if you just like typed kill, it would like do something context specific that might be better. But like the error I was getting wasn't like you didn't specify the flags. It was like there is no process of that name, which is sort of like not the error I would expect if I just like misformatted the command. But I guess there's no reason not to specify -9. I really wanted that dead, so. Okay, so this should be less than e to the minus mu times e mu over 1 plus delta to the 1 plus delta plus, oh yeah, Ubuntu is going to give me a problem report. I will not report it. I should close out of Slack. That might free up some resources. Plus e mu over 1 minus delta to the 1 minus delta. Okay, and okay, and then I want to split things up. So this should be, well, I guess this is equal, but so I can just factor out the e to the mu. And so this is the 1 bit. And then, okay, I'm kind of thinking these other bits, the 1 plus delta and the 1 minus delta, we can handle by like sort of just ignoring them. I'll just round up both and make it like 1 minus delta to the 1 plus delta. And I think I guess that's like not necessarily small when delta is going to 1, but you know, it probably is negligible relative to like this leading term, or what I imagine to be the leading term. I could be wrong. Okay, so then this is like times, oh yeah, this is a minus. This is times e mu to the delta over 1 plus delta. I guess it still has 1 plus delta, plus e mu to the minus delta over 1 minus delta to the 1 minus delta. Okay. Yeah, I wonder, so can we bound this above? So like as delta goes to 1, this is blowing up. This one is like super bounded. This is like essentially a constant. It's like like at delta equals 0, it equals 1, and at delta equals 1, it's 4. So this one's like not doing anything dangerous, but I guess at this one, as delta goes, at 0, this is 1 as well. So near 0, these are both 1, but then as delta goes to 1, it goes to 0 to the 0. So is it blowing up or is it like bounded? Okay, because I guess the bound is actually most interesting. It says analyze it for small delta, but like for super small delta, this is not an interesting bound because this is just 1 and this is just 2. But I guess it's interesting for delta on the order of like 1 over the square root of mu, which I guess is also quite small conceptually. Yeah, I just want to see if I can throw this out. Just say the whole thing is upper bounded by something without these terms. I don't know that I can. So as... Well, actually, I guess this is probably... I think this is bounded. I think like the... like what is the limit of x to the x as x goes to 0? This... I actually don't know what this limit is. So I guess this is the same thing as the limit as x goes to 0 of e to the x times the natural log of x. Okay, and then you can like commute the limit, and then this one should go to 0 because this blows up, but it's like natural log blow up, and okay, so this will go to 0. So I think actually the limit should just equal 1. Okay, so this should be bounded, and this should be bounded. So I should be able to just say the whole thing is less than some constant e to the minus mu. I guess the constant I'm shooting for is 2. I wonder if I can argue that... Is this... I wonder if this thing x to the x is less than 2 in this interval, or greater than 1/2. I guess is what I want. Yeah, because I guess I want a pretty precise bound here. I don't want to like give up anything because I want this bound of 2 times e to the minus c mu delta squared. Okay, I'm just curious though what happens if we throw out these little bits and we just look at e to the e to the mu delta plus e to the mu minus delta. Huh. So I guess we want something like... e to the mu delta plus e to the mu minus delta. We want this to be less than or equal to 2e to the minus mu delta squared. Do we have that? Question mark. So I guess I want like some kind of Taylor expansion of these things by around like delta, like so I guess I can rewrite this as, so I have e mu to the delta. I can rewrite this as like e times 1 plus the natural log of mu times delta, right? Yeah, because this turns into e times mu, and then over here we've got the other one plus e1 plus the natural log mu delta, but negative. And then if we do our Taylor expansion, we're going to like cancel out the even and odd terms as before. So then we have e mu to the delta plus e mu to the minus delta just equals the even terms of these two Taylor expansions with like this bit here. So it should be equal to I guess there's 2 times them, so yeah, it should be like 2 and then times just the odd terms, so, or just the even terms, so 1 plus this thing over, so maybe I'll give this a name. I'll call it like y. So 1 plus y over 1 factorial plus, oh no, sorry, I said the even terms. Y squared over 2 factorial plus y to the 4th over 4 factorial plus dot dot dot. And yeah, so then this is, so we have these like larger factorials, so we can say this whole thing should be less than 2 times e to the y squared. So this is equal to 2e to the 1 plus natural log of mu squared delta squared. And now we have the so we get the delta squared we want. So do we have wait, but I guess we have the wrong sign. Wait, this is totally wrong. Yeah, why do we get minus? Huh. Yeah, why should we get a negative y squared? So I guess only, so the even terms are positive and they survive, and we get this expression. Yeah, I don't know. This is sort of a complicated expression to analyze. Maybe I threw out too much by throwing out these like 1 plus deltas and... Or I guess actually it's just like not the case that you get your bound from these bits. Oh, wait. Am I... This shouldn't be 1 plus delta, 1 minus delta, should it? It should be 1 plus delta mu and 1 minus delta mu. Right. Yeah, this is incorrect, right? Because what is our t is 1 plus delta mu, not 1 plus delta. Okay, so we should have a mu here, and a mu here, and mu's here, and here. And then these cancel. And our true expression should be slightly simpler then, and also slightly more complicated. Just slightly different, I suppose. So the expression we really want to look at, let me zoom in a little more. So we really want to look at is e to the minus mu. Right, yeah, because that's in both of them, and that just depends on the mean. It doesn't depend on like the threshold. And then times e over 1 plus delta to the 1 plus delta mu plus e over 1 minus delta to the 1 minus delta mu. Okay. And let's see. So what then? Maybe we can split this up into mu and mu delta. Oh, okay. I think this is going to work out a little better now. So if we split it up into mu and mu delta, then we can factor out the e. Yeah, so this whole thing is equal to e to the minus mu. And I'll split this up into mu plus delta mu. So we've got e to the mu over 1 plus delta. I guess I'll leave that as 1 plus delta mu. Times e to the delta mu plus e to the mu over now 1 minus delta to the 1 minus delta mu times e to the minus delta mu. Okay, and now this is canceling out. So this e to the minus mu, we can just cancel with these. And we get e to the delta mu over 1 plus delta mu plus e to the minus delta mu over 1 minus delta to the 1 minus delta mu. Okay. And so our goal is to bound it above by this expression. So I feel like we're maybe getting closer. I don't know, actually. This seems very strange. I wonder if we messed up at some point, because, like, to me, this bit doesn't seem very small. Like, if delta is close to... Oh, okay. I guess this is... So we need this to be large to fight with this to get this exponentially small bound. And I guess we have that, because if delta is very small, well, then this is very small as well. Oh, yes. So 1 plus delta. Of course, we have bounds like 1 plus delta is smaller than e to the delta. And of course, the exact same for 1 minus delta, because this actually doesn't depend on delta being positive. Okay, but these bounds go the wrong way, because I can't just replace the denominators with this stuff, because then that would actually, it would shrink the denominators, which would, or it would grow the denominators, which would shrink the whole thing, and we're trying to get an upper bound. So we can't just replace these numbers with these expressions, which would help a lot. But maybe we just want to anyway. Can we argue that we can? So these are very accurate estimates for small delta. But I guess it's probably still cheating to apply them. Yeah, so I can't even replace the numerator with the other one, because I guess they go the exact wrong way in both directions. Okay, but maybe I'll just do an argue, like just make an approximation. So this is approximately equal for delta very small to e to the delta mu over e to the delta 1 plus delta mu plus e to the minus delta mu over e to the minus delta 1 minus delta mu. And then we can cancel some things, and this is exactly equal to e to the minus delta squared mu plus, we would just get exactly what we want. Yeah, okay. Okay. I wonder if there's some like just constant we can put here to make this true. That might be the case. That's why there's a constant here, because this isn't quite true, but you can just introduce a constant to make it true for small delta. But I guess you can't really just make it true, can you? Or no, I guess you can. I guess you can, because delta is delta's like small, so you can't like choose one c that makes it true for all integers, of course, or all real numbers, of course, because this is exponential, this polynomial. But you can choose some integer c that makes it true for all delta between 0 and 1. I think I'll leave the details to I guess the watcher. But yeah, I'll type this up. I think we have a strong enough idea of what we're doing now that yeah, it's got all we need. Okay, so this is 2.3.5. Okay, so by Chernoff bounds, we have that probability of this distance from the mean being greater than or equal to delta mu should be less than or equal to the sum of these two things, which is just this. So e to the minus mu so frac e, no fracking, it's bad, as I understand it. 1 plus delta to the 1 plus delta mu and then just the same thing with minus. Oh yeah, I guess I should copy. Oh, okay. Must have copied the whole line without meaning to. Delete to L. Oh, delete to L again. And then just replace some pluses with minuses. See how that looks. Doesn't like it. Where's the problem? Runaway arguments. So we have the fraction, we have the exponent. This is matching that. Oh, I guess I just don't need that parentheses. Get rid of that. Oh, okay, and then it works. Oh, okay, I need to delete this e to the minus mu as well. And I need to close it. Okay. And what is this equal to? So I'll just write down this next line where I cancel out the e to the mu's. Well, I guess I'll jump to this line, and then I'll make our observation about 1 plus delta and 1 minus delta. Divided by. I need to balance some things out, right? Okay. Okay, so that's the first part, and then I'll just copy paste that. Change some pluses to minuses. Okay, now I make my hand-wavy claim about this bound. So for delta in 0 to 1, we can find C such that 1 plus delta is less than or equal to e to the delta. And the other one. Oh, I want the just to go the other way around, right? Yeah, so I guess the idea is you need sort of like a small c, because so like this is looking like this, of course, but if you scrunch out the c, you can have it look like I wonder if you can get both of these simultaneously. Actually, something is looking a little sketchy here, but I'm just going to move on. It sort of seems like actually whatever C you choose here is like not helping you here. Yeah, I'm actually not sure if we can find one C that does both. I mean, it does seem like this should just be approximately equal, but I don't know. Approximately is maybe doing more work there than I'd like. Put this there. And so I say this is less than or equal to, now this with the C's. Oh wait, but I guess I don't even want the C's. I want them to be, I'll just say for small delta, these are approximately equal. Okay. Okay, and then, so, yeah, so then we have this is approximately equal to, what should be approximately equal to? It should be approximately equal to this. And the other one. Oh, but with a minus here, and a minus here, and a minus here. Oh yeah, so there should be a minus here too. Minus, and then okay, minus there, minus, and then this one is just equal to what we want, equals 2e to the slash mu slash delta squared. Okay, and I guess there's like some work to be done in making like this approximation precise, because we're not assuming delta is like small, we're assuming it's less than 1. So I guess there's some loss on both of these. But I guess you can like just introduce constants. I think the problem is you need a different constant for like both of them. Oh yeah. So like we can choose, yeah, so any constant you choose on one is like hurting on the other. So I guess at the end you need to like have two different constants and like take the maximum of them to like get it correct. Maybe I'll make a note to myself for later, but I don't want to type that up now. But I think if you did that, it would then work out. But for small delta, these are just approximate equalities, and we've got that. Okay, cool. So that's that one. I think the rest in the chapter are hopefully easier. They have fewer coffee cups anyhow. Okay, so in the next one, we've got Poisson distribution near the mean. So let x be Poisson distributed, and then t is between 0 and lambda. We want to show that the probability that we're that far away from the mean is this small. It says combine exercise 2.3.5 with the Poisson limit theorem. Okay. So the Poisson limit theorem, of course, says if you keep adding these things up, you get a Poisson distribution. Okay, so let's say, okay, so for all n, we have probability that Sn minus, so the distance, yeah, I guess I should call it lambda. So Sn minus lambda greater than or equal to t is less than or equal to 2 times x. So this is just the previous exercise. Is it the previous exercise? Oh, it is the previous exercise with t equals delta mu. So then, like, your delta is t over mu. Okay. So maybe I'll make a note. So by the previous exercise, and this is an absolute constant, the c. So and then I guess we can let lambda just kind of vary in Sn. So minus c t squared over lambda. Okay, and then taking the limit as n goes to infinity, we have, and then we just get the this bound. So yeah, because this is approaching a Poisson distribution. I'll just yank the whole thing and just replace it with x. Okay. I guess there's not much to this one, it's just kind of observing that you can take the limit. Okay, yeah, just a 1 coffee cupper. Okay, well, there's a remark now. It'll be a nice break. Okay, so large and small deviations. So exercises 2.3.3 and 2.3.6 indicate 2 different behaviors of the tail of the Poisson distribution. In the small deviation regime near the mean lambda, the tail of Poisson lambda is like that for the normal distribution, and lambda lambda. In the large deviation regime far to the right, the tail is heavier and decays like lambda over t to the t. Okay. Yeah, I guess that's what it's saying. This is like a Gaussian, and it's saying like for these small delta you're behaving like a Gaussian, and yeah, over to the right there's more weight. Okay, so you get like the worst behavior in both regimes. Okay, and I guess it's like just graphing this Poisson, and like if you look close, you're like, oh, that's about normal, but then you look off to the tail, and you're like, oh, that's not normal. Okay, and then let's try to do this last one, normal approximation to Poisson. Oh wait, I typed this up in the problem part, or in between the problem and the solution. Okay. So this is 2.3.8. So let x be Poisson distributed, then show that as lambda goes to infinity, we have that x minus its mean over root lambda is going to the normal distribution. And it says derive this from the central limit theorem and use the fact that the sum of independent Poisson distributions is a Poisson distribution. Okay, so let's just assume that lambda is an integer. So for simplicity, let lambda be an integer. So I guess one could imagine weird behavior happens in between, but I think it's clear that this is a fine assumption to make. If x is distributed Poisson with parameter lambda, then x and let's introduce some other variables. Call lambda or x sub lambda are distributed by Poisson with parameter 1, then this is just the fact that it's saying that the sum of independent Poisson distribution is Poisson distribution. I guess it's sort of a basic fact about this distribution. Same thing holds for the normal distribution, and I guess a lot of distribution people like to think about. And I don't know, I guess I'm using sort of a weird notation to say distributed like this, but I guess it's the one Verschuinen uses, so it makes sense. Okay, so now what do we have? This is distributed like, okay, and then this has mean lambda and standard deviation root lambda. And I guess I'll say mean and variance lambda. And then just therefore by the central limit theorem, we're done. Just type it out. Okay, yeah, so just all right, okay, cool. Oh yeah, and once again, I put this in the wrong place. Okay. Yeah, it seemed like the Chernoff problems were a little easier than the Hofdinger problems. I'm still like a little stuck on that one, like this one. I don't know like if I'm missing something. Like I can't get either my truncation trick or my variance version of Hofdinger's to like work out, but I must just be missing something. But I guess yeah, we're done with our Hofdinger's and Chernoff's chapters now. Yeah, I guess I've already gone a little longer than I intended to, so I'll stop here. But yeah, next time I'll hop in with applications, degrees of random graphs, which is maybe going to be a little funner than this like just kind of theory building. But I guess Chernov's and Hofdinger is just like so important. All right, yeah, thanks everyone for watching. Sorry for the technical difficulties in the middle. I should probably find like a new PDF viewer. I find this one to be like sort of unstable. But I don't know what the optimal one is. Okay, till next time.